Hey everyone, and welcome. Today we're going to jump in and solve some algebra problems that, can look a little wild at first glance. We're talking about equations with those fractional exponents. But I promise you, by the end of this, you'll have the master key to unlock them. Let's get right into it. So take a look at this equation right here. X to the power of 2/3 equals 9. Now, if that little fraction up there makes your brain pause for a second, you are definitely not alone. But here's the thing. Think of it less like a tough problem and more like a fun little puzzle we're about to crack together.
And yeah, that's exactly how we should think about these equations. They aren't necessarily harder than other algebra problems, they're just a new type of puzzle. And like any good puzzle, there's a special key that just makes everything click right into place. So these fractional powers have a name, of course. They're called rational exponents, and really, they're just a kind of shorthand for writing roots and powers, stuff you've probably seen before. The number on the bottom of the fraction, that's the root. The number on top, that's the power. So x to the 2/3 is just a fancy way of saying the cubed root of x all squared. But you know what? We don't have to get all bogged down in writing out radicals. Nope. We have a much slicker, much more elegant tool for this. I like to call it the reciprocal power key, and it is, without a doubt, the single most important technique for blowing through these equations. Okay, so here's the absolute core of the technique. To solve an equation where x is raised to a fraction, like m over n, all you do is raise both sides of the equation to the reciprocal power. And what's the reciprocal? It's just the fraction flipped upside down, so m over n becomes n over m. Simple as that. But why does this actually work? Well, it's all about one of the main rules of exponents. When you raise a power to another power, you just multiply the exponents together. And what happens when you multiply any fraction by its reciprocal? Well, they cancel each other out and just become 1. And that is how we make that tricky fractional exponent just vanish, leaving us with a plain old x on one side. All right, that's enough theory. Let's put our new key to the test, shall we? It's time to unlock a few of these puzzles. We'll start with a nice easy one, and then we'll add a few twists and turns. First up, x to the 1/3 power equals 4. Okay, so what's the reciprocal of 1/3? It's just 3. So we raise both sides to the power of 3. On the left, the exponents cancel out, leaving just x. And on the right, 4 to the power of 3 is 64. And that's it. We're done. See? Super nice and clean. Okay, let's go back to that original puzzle. X to the 2/3 equals 9. The reciprocal of 2/3 is 3/2, so we raise both sides to the 3/2 power. That gives us x equals 9 to the power of 3/2. We take the square root of 9, which is 3, and then cube it to get 27. But wait a minute, hold on. There's a twist here. What if x was negative 27? The cube root of negative 27 is negative 3, right? And what's negative 3 squared? It's also 9. The original equation works. This means we actually have two solutions here, 27 and negative 27. Now, what if the part with the exponent isn't all by itself? Check this one out. The absolute #1 crucial first step is to always isolate the term with the rational exponent. So we'll divide both sides by 2. Okay, now it looks familiar. We apply the reciprocal power, 4/3, to both sides. The cube root of 8 is 2, and 2 to the power of 4 is 16. Just one last quick step. Add 1 to both sides, and we get our answer. X equals 17. So as you can see, this method is really powerful, but there are a couple of really common traps that are easy to fall into. So let's talk about them right now so you can avoid them. The first, and by far the most common trap, is the one we just saw. Totally forgetting about that plus or minus case. It is so easy to find one correct answer and just stop there. But you might be leaving a second, totally valid solution behind. So here's the rule of thumb you gotta remember. If the numerator, the top number of the original exponent, is an even number, you have to check for 2 solutions. Look here, side by side. The cube root of negative 27 is negative 3. But when you square it, and that's the 2 and 2/3, that negative sign just disappears, and you still end up with 9. That's why both of these answers work perfectly. The second trap is way simpler, but it happens all the time, just messing up the reciprocal. Just remember, it's not some complicated thing. The reciprocal of a over b is just b over a. That's it. Just flip it. Okay, so you've pretty much mastered the technique. But I know you might be asking that age-old question, when am I ever going to use this? Well, how about to understand some of the basic laws of life itself? Let's take a quick detour from algebra class over to biology. So, in a field called physiology, scientists are trying to figure out how animals' bodies work. And one of the biggest puzzles for them is how an animal's size, its mass, is related to how much energy it uses, its metabolic rate. And what's amazing is that this relationship is described by a mathematical formula called Kleiber's law. It basically says that an animal's metabolic rate, R, is proportional to its body mass, M, raised to the power of, you guessed it, a rational exponent, 3/4. And this law holds true for almost every animal, from a tiny mouse all the way up to an elephant. So here is a real-world scientific puzzle. Imagine you're a biologist and you just measured the metabolic rate of some newly discovered creature. How could you use that number to figure out its total body mass without even putting it on a scale? You use the exact same tool we've been practicing this whole time, the reciprocal power key. To solve for the mass m, you just raise both sides of that equation to the reciprocal of 3/4, which is 4/3. So the very same key that unlocks your algebra problems also helps unlock the secrets of the natural world. How cool is that? We have built an awesome foundation today. You've got the key, you know about the common traps, but there is one last really fascinating twist to this whole topic. What happens when you do all the math perfectly, you get an answer, you plug it back in, and it seems to work, but it's still somehow the wrong answer? Now, that's not a riddle. It's a very real thing in algebra. These weird phantom answers are called extraneous solutions. And in our next explainer, we are going on a hunt to figure out where they come from and, more importantly, how to spot them.
Thanks for watching.